Ever wondered how rockets work? The concept may seem complex, but it's all about action and reaction. This principle, known as Newton's third law of motion, states that for every action there's an equal and opposite reaction. Now, let's apply this to rockets. Imagine a balloon filled with air. When you let it go, the air rushes out one end, propelling the balloon in the opposite direction. That's a basic demonstration of action and reaction. Rockets function on the same principle, but on a much grander scale. The rocket engine expels mass in the form of hot gases and exhaust products. This expulsion creates a force in the opposite direction, propelling the rocket forward. This force is known as thrust. It's this thrust that pushes the rocket upwards against the force of gravity and into the vast expanse of space. So let's dive into the fascinating world of rockets and explore how they work. The power of a rocket comes from its propellant, which is a combination of fuel and oxidizer. Now, what exactly does this mean? Well, let's break it down. Fuel, in the context of rockets, is typically a hydrocarbon-based substance like kerosene or liquid hydrogen. This is the stuff that gets ignited and provides the energy needed for liftoff. On the other hand, the oxidizer is a chemical that provides the oxygen necessary for combustion. It's kind of like the breath to the fuel's fire. These two elements, fuel and oxidizer, are stored in separate tanks within the rocket. This is crucial because keeping them apart until the precise moment of ignition ensures controlled combustion, preventing premature explosions. When they finally meet and react inside the rocket engine, the result is a tremendous release of energy in the form of hot gases and exhaust products. The combination of fuel and oxidizer is what gives rockets their explosive power. Once the rocket is in flight, the fuel and oxidizer mix and ignite. This crucial step, known as combustion, happens inside the rocket engine. Picture this: the propellants, fuel, and oxidizer, earlier stored in separate tanks, are now combined in a chamber. This mixture is then subjected to a spark or a heat source, resulting in ignition. This combustion process is rather explosive and releases a tremendous amount of energy. But how does this energy manifest? It takes the form of hot gases and exhaust products. These are not your everyday gases. They are incredibly hot, with temperatures reaching thousands of degrees. And what about the exhaust products? They are the remnants of the fuel and oxidizer post-combustion. These substances, once useful, are now waste and are expelled out of the rocket. This combustion process is what propels the rocket forward. It's all about harnessing the energy from the controlled explosion inside the rocket and using it to push the rocket up and away from Earth's surface. The propulsion of a rocket is all about thrust and nozzle design. It's a spectacular dance of physics and engineering, where every small detail can have a big impact on the performance of the rocket. Let's delve into it. Thrust is the force that propels the rocket into space. It's created when the combustion process in the rocket engine produces hot gases, which are expelled out the back of the rocket. This expulsion of gases, according to Newton's third law, generates a force in the opposite direction, pushing the rocket forward. But how does the nozzle design come into play? The nozzle is specifically crafted to accelerate these exhaust gases to extremely high speeds. Its shape is crucial in optimizing the efficiency of the rocket engine. A well-designed nozzle can effectively convert the energy of the combustion process into kinetic energy, increasing the speed and efficiency of the rocket. So, the nozzle design plays a crucial role in the rocket's speed and efficiency. Rockets don't just go straight up, they need to be steered and stabilized. You see, sending a rocket into space isn't as simple as lighting the fuse and hoping for the best. It's a delicate dance of physics and engineering, and control and guidance play a crucial part in this performance. Let's start with fins. These are like the rudders of a ship, helping to steer the rocket and maintain its stability. They're especially crucial during the initial ascent when the rocket is moving through Earth's atmosphere. Then there's the aerodynamic design. The sleek, streamlined shape of a rocket isn't just for show. It reduces air resistance, making it easier for the rocket to ascend. But perhaps the most sophisticated aspect of rocket control are the onboard control systems. These systems can adjust the direction of thrust or even the orientation of the rocket in real time. They're like the brain of the rocket, making split-second decisions based on a myriad of data inputs. These control mechanisms ensure the rocket reaches its intended destination. Rockets are not just one big piece, they're composed of multiple stages. Imagine each stage of a rocket as a separate vehicle, each with its own engine and propellant. Now, why do we need these stages? Well, the key lies in overcoming Earth's gravity and achieving the desired speed. As a rocket ascends, it burns fuel, and as a result, it gets lighter. But here's the catch. A significant portion of the rocket's weight is its fuel, so once a stage exhausts its fuel, it becomes a dead weight. That's where staging comes into play. This process involves jettisoning or shedding each stage when its fuel is depleted. By doing so, the rocket gets lighter and the remaining stages can continue the journey with less weight to carry. This clever strategy, often called staging, is a crucial part of rocket science. It's an ingenious way of boosting the rocket's efficiency. Staging is the process that allows rockets to reach higher altitudes and speeds. Every rocket has a mission, and that mission is carried in its payload. Now, you may be wondering, what exactly is a payload? Well, a payload can be anything a rocket carries beyond what is necessary for its operation. This could include satellites, astronauts, scientific instruments, or cargo. Each payload is carefully designed and selected based on the mission's objectives. So, where does this payload go? The payload is typically housed in the top stage of the rocket. You can think of it as the crown jewel of the mission. It's protected within the rocket during the turbulent journey through Earth's atmosphere. Once the lower stages have done their job, propelling the rocket to the right altitude and velocity, the payload is released into space. It's like a bird finally being released from its cage, ready to start its own journey. Remember, the payload is the reason for the rocket's journey. Rockets are used for a variety of missions, from reaching specific orbits to exploring deep space. Just as a ship sails towards a chosen destination, a rocket is also guided towards a specific goal. Depending upon the mission, the rocket may be required to reach a particular orbit around Earth, journey to another celestial body like the Moon or Mars, or even exit Earth's orbit entirely to delve into the mysteries of deep space. Let's take a closer look at these different types of missions. If a rocket's mission is to reach a specific orbit around Earth, it's usually to deploy a satellite. This could be a weather satellite to help meteorologists predict storms, a communications satellite to assist with global connectivity, or a scientific satellite to gather data about our planet and its environment. Now, if a rocket's destination is another celestial body, we're talking about interplanetary missions. This could involve sending rovers to Mars to gather data about the red planet's geology and climate, or sending probes to the outer planets and beyond to help us understand the far reaches of our solar system. But what if the rocket's mission is to explore deep space? Well, that's where things get really interesting. These missions might involve sending spacecraft to study distant stars, galaxies, and other cosmic phenomena that lie beyond the reach of our telescopes. The data gathered could help scientists answer fundamental questions about the nature of the universe and our place within it. And let's not forget about the tasks that rockets perform once they reach their destinations. Once a satellite is in its designated orbit, it can start its work, be it weather monitoring, telecommunications, or scientific research. Similarly, a rover on Mars can begin its exploration and data gathering, while a deep space probe can start sending back images and data from the farthest corners of the cosmos. And so the journey of a rocket is not just about the launch or the voyage, but also about the critical tasks it performs in space. Whether it's deploying satellites or conducting scientific experiments, rockets make space exploration possible. Some rockets or their payloads need to return to Earth, which involves re-entry and landing. This is where things get intense. The re-entry phase starts when the rocket or spacecraft begins its descent back into the Earth's atmosphere. The speed and angle of re-entry are critical. Enter too steeply and the craft could burn up due to the extreme heat generated by friction with the atmosphere. Enter too shallowly and it could bounce off the atmosphere back into space. Once the optimal entry angle is achieved, the craft must withstand temperatures that can reach up to 3,000 degrees Celsius. This is where the heat shield comes into play. This specially designed barrier absorbs and dissipates the heat, protecting the craft and its occupants. Now comes the landing phase. Depending on the design, the craft may deploy parachutes to slow its descent or use retro rockets to make a controlled touchdown. Either way, precision is key. From launch to re-entry, the journey of a rocket is a testament to human ingenuity and the power of science.